Yeah, good afternoon. Welcome again. In this session, we are going to have the talk on the temperature modeling, and our Singh sir, Professor N Singh, who had done extensive work from crust, mantle, core processes about the thermal exchange, and also even at the small scale where this in the OSL dating, whether due to faulting, the time of faulting, um, whether the temperature will reach up to the resetting time or not. So at the different scale, he has done the modeling processes besides many other aspects, and we requested him to give a talk on the different aspect of the temperature modeling in the Earth system sciences. So I request sir to please discuss the role of temperatures in geomorphology. Thank you.
Uh, I think after lunch, everybody feels sleepy. I also feel very sleepy. So, but when Ramendra asked me to speak, I have no choice. Okay. So this topic in your announcement is different, but then it was supposed to be tomorrow. So it has been preponed. So the topic has been a little bit generalized to suit today's morning lectures too. So let us look. I plan to do why to bother about temperatures in geomorphology? After all, you have a book called Mechanics and Chemistry of Landscape. So, uh, so I will give some justification and then discuss how temperature changes in the earth. I shall go to mention how sun's heat, radiogenic heat in the earth, cooling of geological objects, heat due to dissipation, all these affect geomorphology. So I intend to say something about that. Okay. Now, uh, the how to remain, how to show this. I want to show you one. I have recently learned to do it, whether it's come or not. I don't know. Don't come. Don't come. Okay. So this was a discussion about cracking of the earth, and the sentence which I found interesting was that standing on a high vantage point, I overlook a vast, rocky, snow-covered rift valley. Fissures and cracks scar the landscape filled with water so clear I can see hundreds of coins winking at me from several meters below. The sentence which appealed me will come little later. These cracks in the land were not always there. Forces from below have slowly broken the rocks apart over thousands of years. The largest crack actually marks the gradual separation of two continents, a dramatic example of our landscape. It always struck me that rocks are incredibly strong, unbreakable almost. But walking around this park leaves me a strong impression how fragile and changeable the earth surface is really. I think sentence which surprised me. I, I asked geologist from the University of Iceland about this, and his answer surprises me. All the physical movements in nature we see on the earth's surface are extremely feeble compared to what is happening deep below. Add some intense heat into the mix and the process slowly ripping apart onto landscape are same forces that contribute eruption. So add little bit heat and you see how things fall apart. So it's important of heat I picked up from here. So can you just okay. and then also एक और दिखा दो वो भी हाँ and then I looked in the yesterday in Google, did anybody give a talk on temperature in geomorphology? I ended up with this slide. It's a 4 minutes, so I think you have a better introduction than what I would have given. This is by, I think, Haggett, or no, Knight. यही होगा क्या? Okay, ये प्रॉब्लम है तो जाने दो.
Hello, I'm Peter Knight, and this is number 6 in our series of short lectures on geomorphology. The aim of this lecture is to introduce very briefly some basic ideas about temperature in geomorphology. My key point is that temperature is important, and that this is partly because the properties of materials vary with temperature. Specifically, I'd like you to think about these two questions. How does temperature influence geomorphic processes, and what determines temperature regimes in different environments? Temperature controls the structure of materials, their properties, and their effects. For water, for example, when it's cold, it's a solid. When it's warm, it's liquid, and it can boil or evaporate and become a gas. In each of those phases or structures, water has different properties, such as its hardness, density, or viscosity. And because of those properties, the material, for example water or ice, can have very different effects. We've already encountered the effect of temperature on materials and processes in different geomorphic contexts. Temperature very clearly drives volcanic processes. It drives the buoyancy that creates these cumulus clouds, and it determines whether rock is liquid or solid. Temperature also controls the rate and style of both chemical and physical weathering processes. In all these examples, the nature of the process and the rate of the process depend very much on the temperature of the environment or of the materials involved. We encountered temperature as a control in one of our earlier case studies when we saw that the flow of ice depends partly on the hardness of the ice, which in turn depends largely on temperature, as described here in Glen's flow law. We also saw that temperature was a key control on the friction that can retard glacier sliding, because basal water pressure is partly temperature dependent. The striations, crescentic gouges, and other signs of glacial erosion on this bedrock in Greenland tell us that the glacier that used to be here was sliding over the rock, and that, in turn, tells us about its basal thermal regime. Cold-based glaciers move differently from warm-based ones, and so have a different geomorphic signature. Sometimes temperature acts as a direct control on process. In other situations, it can be an indirect control, affecting things such as soil moisture or vegetation, which themselves can influence geomorphology. It's also significant at the largest scales and at the longest time scales, for example in controlling the growth and decay of ice sheets, which in turn affect sea level. You can find the effect of temperature in almost any landform or landscape. It's important, therefore, to understand broadly what controls temperature. Different sources of energy include solar energy, geothermal energy, and energy generated by the processes themselves. For example, the movement of water, ice, or other materials generates heat from friction that can maintain mechanisms of motion, erosion, or weathering. The distribution of this energy is an important geographical control on geomorphic processes. A geomorphological map of subglacial landforms, for example, would be a very close mirror of a map of basal temperatures. Those of you who will have the delight of a real face-to-face lecture from me on this topic will go through this in more detail in class, but for those of you watching this on video only, here's a quick list of some of the factors that control local ambient temperatures in many geomorphological settings. Essentially, these are controls on local climate or microclimate, which in turn has a significant impact on processes and landforms. And we need to remember that it isn't just the absolute temperature that matters. The range of temperature fluctuations and the timescale over which those fluctuations occur is also important. For example, in a permafrost environment, it's not simply the low temperature that matters to frost shattering or solifluction, but also the range and, even more important, the frequency of fluctuations above and below the critical freezing threshold. These microclimatic variations, or if you like, the geography of energy supply, can have complex effects. For example, whether a hill slope faces towards or away from the sun, its aspect, will have a big impact on the amount of solar energy received, and hence on the absolute temperature and on the range, seasonal variability, and diurnal variability of temperature. This will impact moisture availability, vegetation growth, soil characteristics, and hence both the amount of surface runoff and the erodibility of the soil. So opposite sides of a valley might experience very different geomorphic processes and could develop pronounced valley asymmetry as a result of variations in erosion that can be traced back to temperature regimes controlled by aspect. There are lots of examples that you can find in the geomorphic literature to illustrate these ideas. Here's a paper that takes into account the effect of variations in energy conditions along a hill slope in Uganda. And here, slightly more exotic, is a paper that looks at the effect of aspect on mass movements and slope evolution on Mars. So, in conclusion, temperature is an important variable in geomorphology. It drives geomorphic processes and it controls the properties of materials. Temperature is controlled by energy supply, and the distribution of energy is at the heart of physical geography.
Okay. So, what is temperature? What do we mean by temperature? Pardon? Little more in terms of energy.
So, degree of measure of hotness and coldness. Is this the temperature?
Yeah, but could you convert that in terms of energy? Any object is made of atoms.
Yeah.
They vibrate.
By weight, right?
Each has kinetic energy.
Right.
What is temperature?
It will oscillate more about its equilibrium position when it have high.
That is more energy, less energy. What is temperature? Yeah, all we are talking energy, but I want a relation between energy and temperature. Pardon?
Thermal energy.
Well, energy is defined as average kinetic energy in the universe. It's average. The difference between heat and temperature is, think of a beaker of water. It's filled with water. So total water you can think of heat. And height of the water in that beaker you can think of temperature. So that is difference between total energy and temperature. So it's sort of average property of that. So now in this slide you saw there was more focus on how the solar energy is getting redistributed through a variety of hydrological processes and controlling the Earth's surface. My focus will be what is happening below the surface and how it affects it. So I will not describe this. Okay, there is another one. It's a physicist game. And to introduce the historical background for it, see there was judges say what is called due process. Like what is happening in Nirvaya's case, due process is going on. So in a court of law, decision is arrived by due process. So when I was reading due process, there was frequent reference to Earth's surface science. And it was interesting to see, like the Earth's surface, Supreme Court due process jurisprudence is product of gradual case-by-case process of our accretion. So case-by-case study. So in geomorphology also you have case-by-case study. We go to very detailed knowledge of what goes on from grain scale to a handheld scale to that. So court due process was like that. Then he goes and say, lawyers, judges and most academics consume the Supreme Court's due process jurisprudence the same way it is produced. Like traditional geologists, they work within a discrete chunks, examining at close range individual cases such as Chambers versus Mississippi, or constitutional dimension of excluding hearsay offered by criminal defendant, or cluster of cases, etc. By contrast, he, in his article, A Perspective on the Supreme Court Due Process, that is scholarly equivalent of physicist geologist view of Earth's surface. So even in court, he said there is a case-by-case study and there is a physicist geologist view of the Earth's surface. He makes us look at the big picture, giving us a panoramic view across wide range of criminal procedure issue from investigation to sentencing and covering more. So even law also, you have one abstract art and other landscape painting. Now, role of temperature need to be understood from abstract painting from the painting point of view. Now, what was this physicist invading? So, okay. Oh my God, my slide gone. Okay, can you show that? Now, in New York Times, an article came, physicists are invading geologist domain. And that article is very interesting. It's good for Earth surface scientists to know. This is about 99 article, physicists invading geologist turf. Now, William Dietrich, everybody knows in this audience, because without him, very difficult to think of quantitative geomorphology. William Dietrich has walked, driven and flown over more natural landscape than he can remember. As a veteran geomorphologist, he has studied how everything from plop of a raindrop to mighty landslides and geological uplift have shaped the face of the planet. So when he admits to growing influence of his field of an insurgent group of physicists, mathematicians and engineers with all encompassing mathematical theories, but hardly any field experience, the earth almost becomes. So all these people who talk of physicists, they hardly have any field experience. Now to the end, in the end I want to show you what he says. For all the insights of the new research, geologists are far from abandoning their worldview. In fact, they too are using satellite data to perform detailed computer calculations of how rain and wind erode one particular landscape into another time. But even there, Dr. Dietrich says, the physics-oriented researches have inspired discoveries of order amidst reductionist detail. The places where they accomplish that will, I think, have a lasting influence on how we think about the planet. So Dr. Dietrich admits the role of the physicist's view of the Earth's surface. So I urge that please keep both views in your mind, and that will be quite useful. Okay. So now, what is happening in the Earth's interior? If you look at this scale, you are having from spatial scale from 10 to the minus kilometers all the way here, impact, earthquakes, volcanoes, earthquake coupling, post-seismic rebound, tetracycle, post-glacial boundary. So from mantle all the way to impacts, a variety of transient, steady-state phenomena are happening in the Earth's interior, and all affect the Earth's surface some way or another. So now, just to tell you how these are coupled, there was an article called Thermodynamics of the Himalayan Origins by K.V. Hodge. He looked at the problem like this, that suppose in Himalaya, I put energy. How will Himalaya respond? Will it rise? Will it deform? Will it metamorphose? Will it melt? So there are a variety of geophysical processes by which Himalaya can respond. So how it will respond? So he draw a diagram, and here you find how energy is being pumped from, say, plate convergence, this dark one. They are giving the energy, this plus, plus, plus. And the energy is being dissipated from the shear heating, radioactive decay, igneous process, metamorphism, erosion, tectonics, and lithospheric thickening. So, and then the energy is getting stored into crustal thickening, prograde metamorphism and ataxics. So, when you put some energy from here, here, why I am pushing energy? Because that I will relate to temperature much more. Then how Himalaya will respond? Will there be more shear heating? Will there be more erosion by uplift? So such questions are also as important as describing in detail what happens in a locality. Okay, but if you want to do this, you have to use what Bertrand Russell said about physics, that physics is mathematical not because we know so much about physical world, because we know so little. It is only the mathematical properties that we can discover. So when I do a physical problem, unless I can describe it mathematically, I don't know how to measure it even. So you need to use mathematical language. And that's why Dr. Jan first day asked that we should bring this point. Actually, one can quote Feynman, people who wish to analyze nature without using mathematics must settle for a reduced understanding. So unless you use mathematics on your whatever data you collect, settle for reduced understanding. You can't, somebody else will derive much more from your data. Okay. So first thing is, when I get some idea, I must convert into mathematical language if I want to do that. So in my case, today, I am interested about temperature. Temperature I will divide into two parts, steady state and transient part. Steady state, like what is this thermal structure of the earth crust, which I will perturb. So how do I find? I will look at how heat is being generated and how heat is being dissipated. I will balance them and get it. And transient heat, solar heat, earthquake rupture, sand dikes, metamorphic reaction, dissipation of deformation. So I hope I will be able to make some point on that. So the hero of today's talk is Fourier. Fourier was a Frenchman. He was not a very privileged from class. He was from, it took long time for him to become fellow of the French Academy. But then he was with Napoleon and finally he rose to very top. Now he developed a theory of heat conduction by which we can find out how temperature can be distributed in a body if I put some heat in that. So there are two principles involved in calculating temperature. One is called conservation of energy and another is called constitutive relation. See, many times when you study the hill-slope process, etc., your equations are exactly the same. D is replaced by H and your equation remains exactly the same. Of course, here K was thermal conductivity, there you will call diffusivity. So, Fourier developed this theory and then it was applied. So, combining these two, we end up getting this differential equation. This is called diffusion equation and this is called heat diffusivity. Now, this equation is used to find out temperature in a system if I perturb it by some process. How do I perturb it? I can erode it from top, I can bring a heated body, I can compress it, change radiogenic index. So, there are a variety of processes by which I can perturb it. In order to solve this, I need to have two conditions. I must be able to say from where I am starting and what is the boundary condition. And boundary conditions tell me how the system is interacting with its environment. Suppose I have a crust, then how it is interacting with the mantle and how it is interacting with the atmosphere. So these boundary conditions I have to prescribe. And generally there are three types of boundary conditions in the problem. One is that you give temperature, second is you can give flux, third is you can give combination of that. And these three can model all kinds of phenomena which you can come across. So now I want to apply this to a very simple problem, because that problem will take me to problem of the fault heat, which I was going to talk tomorrow. So this is the problem. sorry, before that, let me find out how do you find thermal structure of this. Suppose continent, I want to find structure. So I make first assumption, it is steady, so time goes. Then I say it is only function of vertical. So x and y go, only z remain. Then I say the only source of heat is radiogenic heat. So I get this term. I get this term radiogenic heat, and I have this simple equation. I assume that surface temperature is 0, and I know that at the base of the crust, what is the heat flux. So if I want to find geotherm, I will proceed in the way. So for that, what I need what is the conductivity, what is the radiogenic heat, and what is the basal heat flux. Now, how do I get conductivity? I can take different rocks, go to the lab, measure them. So granite, all kinds of material, and then from seismology, I know what is the average composition of the crust, and I can get the value K. How do I get radiogenic heat? This has been a big problem because we don't have samples all. Of course, now since a lot of lower crust is over crust, so we can go along the surface and find out. So basically, this problem in 60s was solved like that, we will go to the field, put little borehole, measure heat flow there, measure radiogenic heat there. So a linear relationship was found out. So in order to find a linear relationship, two models were given, that crust has a thin layer, a thin layer of radiogenic layer with constant value, and below that there is no radiogenic heat. Another was there is the exponential model, maximum at the Earth's surface, and it goes on decreasing, and that linear slope was used. So based on these two models, thermal structure have been made for different continents. So this is one way of calculating thermal structure, steady thermal structure, one-dimensional in the crust. Now, if you are in South India and you want to find out and ask, all the rocks have been eroded, you are in the Proterozoic or earlier time, what would have been geotherm then? Now, so here I can say surface temperature anyway would be 0 then also. With 10-20 degree doesn't matter between friends, or when temperatures are of the order of 600 degrees centigrade, temperature taken as 0. Conductivity we can think of because rocks are still exposed. How to find heat flux? Now then the argument can be that Earth was going on mantle convection. I know how the Earth has been cooling. See, how Earth has been cooling. So I know how the mantle heat flux has been changing over period of time. I can use that. I can start with initial Earth, run mantle convection, and find out at that time what was it. So based on that, again I can construct the geotherm. Now, like okay, so like that in a paper, Ganguly and I and some people have worked out how the geotherm will look like. So this is one typical way of creating geotherm, which we use for the broad study of the Earth. Now let us come to near the surface. This is from Anderson. On the Earth's surface, we have daily variation, all kinds of temperature variations are there, and depending upon the wavelength, depending upon the time period, one can find out how deep it will be penetrating. Actually, the solution is given like that. This term shows that it will be decreasing with depth. This will show it will have time period. So surface temperature will go on varying like that. Now here you will notice that say from 15 to 45, that kind of variation you are. But as you go deeper and deeper, this will go on decreasing. Now, so I can find out temperature. Now, what use it is? What will be use of such a temperature variation? Now, if I have a rock and I go on daily subjecting to it this thermal fluctuation, what will happen to that rock? First thing, if I heat it up, it will expand. If I cool it, it will contract. So this cycle will go on. In one of the last slides, I will show you that how it will lead to totally cracking of rocks. even if these are very small stresses, but they are very devastating over a period for the rocks. So if near surface, you can calculate it. This is again the solution of this equation. So this is the temperature is going. The calculation has been shown what is going to be changed in the near surface region, and this term, this subcritical crack growth and catastrophic crack growth. This is a very important. See, when earthquake takes place, we generally say that the shear stress must exceed some critical point before slip takes place. But it has been shown that even if it is subcritical, still small growths go on increasing, and over a period of time they can break the rock. So you don't have to have a very high stress to do that. So even such a small thermoelastic resistance. So one of the reasons to calculate temperature will be that we can find out how to break the surface rocks into soil and whether. Now, in subcritical growth, if I have a size of the crack is A, so generally that crack size used to increase when this critical stress will become more than actual stress becomes more than that. Actually, if a rock cracks, there are three modes of cracking. One is normal to that, like tension. Another is slip, two shear type and one normal type. So here it is a normal type, and this finally when temperature varies, this term enters. So temperature you can use to find out how the crack will grow with time. So such calculations are done. Okay. Next thing I want to show what is called flash heating, like your camera, flash heating. Now flash heating is required for your dating. When you do OSL and all that, you need to find out when your sample was subjected to some kind of flash heating. Now, good example of flash heating is how we make Xerox machine. We generate light. For short time, it heats the paper, and in the meantime, copy is done. So the mathematics of Xerox machine is exactly same as mathematics of the fault heat. So I found this analogy, so you might like to look at how they do that. Now, in a machine, we want a temperature to rise like that. In order to get that, I will give heat flux like that. So there will be some time where I will give heat flux. So I have a relation between heat flux and heat temperature. So if there is a heat flux at the fault, now heat flux comes from shear heating. The slip generates frictional heat. That heat I want to raise temperature to such extent that it will reset OSL clock. So how the Xerox machine is done? Now in a Xerox machine, though paper is very thin, but in mathematics is taken as semi-infinite half space, as if it is from 0 to infinity. Now material taken, I'll show. So the relation between, suppose I give a unit heat flux, then temperature is going to be changed like that. Now, and if my heat flux is varying with time, then this is the relationship. Now, so here, if I give heat flux that from 0 to some time it is increasing, and this time it is decreasing, so that I have a heat pulse, then temperature is going to be like that. And from here, you can calculate that what should be the maximum heat flux I give in my flash bulb. So you will notice that exactly the same mathematics get applied to the earthquake rupture. I will go see. So let us go to earthquake rupture, where you have frictional heating. So frictional heating is temperature, shear stress times strain rate is the heat flux. So I need to find out what is the shear stress and what is the shear strain. Shear stress just at the onset of slip is proportional to normal stress, like when you have a slide on an inclined plane. So this is the normal stress, this is shear stress, mu is the coefficient of friction, P is the pore pressure. So from here, so suppose if my plane is at 10 kilometer, I know how to calculate this, and then I know the frictional coefficient, then I can find out what will be the shear stress, and for different shear strain rate, I can calculate what will be the heat flux. So same logic, by which it will slide. So coefficient of friction can be obtained by experiments which have been done. Unfortunately, lab experiments give very high value, but in nature it is not so high. So let us take, you recall in Xerox I had a function like that. In case of earthquake, my fluxion will be in nucleation, there will be velocity will be increasing, then it will remain constant for some time and then it will decelerate. So heat flux will have this time dependence, increasing, constant and decrease. So there was a paper published long back where such calculation, from here you can calculate heat flux. Heat flux is here, velocity has given earlier. So it will be increasing, remain the same, decreasing. We solve heat conduction equation. And here are the calculations. That suppose I have a different material of this is the thickness of the layer, thickness of the zone where heating is taking place. So you find that temperature can get as high as 1400 centigrade, but look at this scale. This is seconds. So in 1 second. Now this will not lead to any metamorphism. No mineral transformation will take place, but photons will be affected. Clock will be reset. So if you look at rock, you will not find what is that, malt to mineralite, those minerals which are found. But for dating purpose, so all kind, even by changing things, you can find out that temperatures are still high. Now one can make more generalized history. Now in this there is no effect of pore pressure, but pore pressure effects has been also what happened, the flash heating we took on the whole fault, but actually fault is not, everything is not in contact, only some patches are in contact. So even for such calculation, temperature can rise up to say up to, in some cases it can rise up to 1000 degrees centigrade. So even if the whole fault is not in contact, only patches are in contact, still temperature can rise. Okay, now let's.
The region over which temperature would be this high? What would be the width of the region over which the temperature would be this high?
2 centimeters.
Okay, so if you are away from that, then your sample is not affected, is it? If you are away from that fault plane, slightly away, then you are not.
No, your sample can be little away, but heat will diffuse.
Yeah, but then temperature will also go down.
So
and
the issue is that for OSL gate, you need 500-600 degrees centigrade.
Okay.
So even if your sample is away from the fault cause,
Okay.
still it will be reset.
Okay. But typically looking at the sample, you would be able to figure out if there is fault running close by, and you'll be able to make a judgment.
Yeah, generally they take close to the fault.
Okay.
Actually, this is the minimum. If you keep little, as you notice, as you are increasing thickness, temperature was rising. If that thickness was rising, because more heat will be generated.
Okay.
Because then you increase the slip also. See, you have to balance the thickness,
Right.
slip velocity, those properties of the minerals, cause rocks. This was simple calculation.
Okay.
to show that temperature will rise more than 500-600 degrees.
Thank you.
But if you put water, that will dissipate the heat. Okay. So let us go to next place of sudden heating called sand dikes. So there it was frictional heat. Here it will be viscous heat because sand dike is thick, and we know that things move. When sand dikes were in place, things move. So here we have to convert the formation energy into heat energy. Now here, before I come to sand dike, there is a how the viscous dissipation in the earth becomes important. So if you have a length scale and time scale, so if time is large, then you get conductive dissipation. If time scale is small and length is small, you will get more viscous dissipation. So in metamorphic literature also this has been discussed. So
I could not understand this last point.
no, the one is that I'll come little later. I'm not able to recall. See, one happens where you have viscous dissipation.
Which are happening over.
Okay. Now I recall.
Yeah.
See, in this regime, you have mostly conduction taking place. The temperature distribution is controlled by conduction.
When the process is having a relatively short length scale and longer time scale,
yeah.
then conduction.
And this scale, you have viscous heating effect. See, you write heat conduction equation, add the viscous heating term,
Right.
and then you ask when viscous heating term becomes important. And rest of the place, heat will be dissipated by heat conduction.
Yes. Okay. I'm asking this question because in the initial on a few slides, you had these very interesting plots where you had these processes and their time scales, and there it seemed like there was a certain slope right in the beginning. One of the first few plots, you had this impact cratering and then earthquakes and. Yeah, एकदम पहला एक या दो slides. It will be much. I'm sorry if you escape and. नहीं है आप थोड़ा. I'll show you. Yeah, that's the one.
Oh, earlier one.
This is the one.
Oh, that
now you see. No, yeah. So now if you look at this graph, seems like there is a slope. Like you see all these processes. So I am trying to understand how does this relate to your last, the one that we are discussing.
You see, this is a schematic. I don't think that anybody has put it. It's a schematic.
No, schematic. Still, you see that as the time scale increases, spatial scale increases, the time scale also increase, which tells you about some velocity. There is some characteristic velocity because if you divide the time spatial scale, the velocity of some signal which can travel across the system.
Nobody has yet looked. This is a schematic diagram.
No, but the numbers are incorrect. You are saying, or they are correct? Pardon? The numbers are correct, right? That spatial scale when you were talking about viscous flow happening.
Like in the case of mantle convection, your characteristic will be, say, mantle convection time scale is 200 million years and thousands of kilometers.
And that's because mantle has a typical flow rates, right? Their ratio will give you the flow rate, and this ratio at the slope of the curve is something like that ratio, right?
See, but I'm just surprised that the impact you are having from here to there.
Yeah.
Earthquakes you are having from here to there. As far as, from very slow earthquakes to very sudden. So I have not seen anybody discussing the
No, no, I also have not seen, but I clearly see a slope. That's what I'm pointing out.
Yeah,
Maybe
but-
someone has not discussed, but there is clearly some trend. I mean, that's not a
no,
good
if
answer
you-
to me that,
if
you know.
think in terms
Yeah.
of hierarchy of processes.
Yes.
So suppose you say that Mendel convention leads to plate tectonics,
Right, right.
plate tectonics to boundary zone to magmatic activity, volcanic activity to earthquakes.
Right, right,
If
right.
you think of hierarchy of going,
Yes.
so one can work that out, but I have not seen any work
Okay,
where
okay, okay, okay.
hierarchical behavior of the earth done theoretically. It is understood that mantle convection will stress the region and energy will be accumulating,
Sure,
then
sure,
suddenly released. But I have not seen where hierarchy,
Okay, okay, okay.
anybody
Like processes
quantitatively
at different
describe the
scale,
hierarchy.
they are processes at different scale and different time, spatial and time scale, they are talking to each other and how.
Yeah. So these scales have been discussed, but
Uh,
no quantitative way
Okay, okay, okay.
of a model where you really
uh-huh.
go from largest scale to
Okay,
grain
Okay,
size scale. That,
Okay.
see, in physics, you have either statistical mechanics
Mhm.
or you have a macroscopy. So those two get connected easily. But suppose in physics you start from statistical mechanics to mesoscopic, all hierarchy. So maybe when those development take place in our culture.
Thank you.
This was to show fashion. Next, next, next. Okay. So in the case of sand dike, the problem is, see, whenever you have to solve a problem, you have to idealize it. Sand dike may have any shape, but then the amount of energy you have to spend in solving that is very, or maybe not worth it. So you idealize sand dike to this kind of a problem, that it is it's a thin problem. So there is a pressure given here, pressure is given there. Using that, you find out what kind of flow will take place. So earlier, you recall, we had tau minus strain rate to generate heat at a fault. Here, viscosity times strain. Strain, of course, strain rate. And this is the expression. So now, in order to calculate, I need velocity. Now, I will take very simple velocity because I am doing calculation for a simple case. So I assume that velocity is just linear. So that this becomes constant. So it is u max divided by the width. Now the question was, how do you get maximum velocity? How to know maximum velocity in case of sand dike? We were not there, no measurement done. So the people who work on fracture mechanics and others say, if you have a surface and if it is elastic, then elastic you have Rayleigh wave and Rull wave, body wave. Forget body wave, you have a Rayleigh wave and Love wave. So it was shown. See, so maximum velocity has been estimated based on experimental background as half of the Rayleigh velocity. So in a sand dike, what will maximum velocity will be almost half of the Rayleigh velocity. And half of the Rayleigh velocity, and what is Rayleigh velocity? Rayleigh velocity is about 0.92 of the shear wave velocity. So using this number, we can find out what will be U max, width we can know, viscosity, then, so this we know. How to know viscosity? I think that was the tough problem. Here was that how there is a viscosity for steady state slow flow. Now when dike in place is not steady, it's a dynamic viscosity. things are moving very fast. So we found out a paper which was, this was for Rayleigh wave for viscosity. Heat capacity is no problem. Viscosity was a problem. Now, people who had ruled out this possibility, they had taken viscosity, this value. This value will not give you. Then we found out a experiment was done by Kawamura for various confining pressure. And this was the coefficient of viscosity which we took. And based on this, how the viscosity was calculated, there they were. Then we solve what will be the temperature rise. So we ignore diffusion, say things is so fast. Now imagine in case of Xerox machine, a paper was taken as a half space. So for short time, it doesn't matter what is the big distance. So diffusion was ignored, and so change in temperature is by heat given in. So by substituting those, by giving value, we found out that even a sand type temperature can be about 600, 550 degrees centigrade. This is good enough to change the, reset the clock. But here the important thing was how to take this viscosity, but for that experimental work, you couldn't have taken that. Pardon?
Same regime that these experiments were done in the same pressure regime that you would expect in this kind of things. The pressure temperature regime, at which do they depend on pressure and temperature?
No, the temperature dependence was not taken.
Is this temperature
Only confining pressure was there. Temperature dependence was not taken.
But this
So
confining
it may
pressure is
change.
also in the actual problem. Confining pressure is known to some extent, is it? In the actual sand dike problem, the confining pressure is known, like when.
Oh yeah, this is taking at depth,
Okay.
not
Okay,
at
okay.
the surface.
Okay.
So they were later on exposed. Later on dug and taken out. It was confined.
So you know the depth.
Yeah, but the point of temperature measurement of viscosity could depend on temperature. That was not taken. And if that lowers the viscosity,
Right.
then it will be a problem for this level.
Right.
But that was not.
Yeah.
Oh, okay. So in our this is the work of Dr. Tyagi, who did a PhD with Dr. Singhvi. So for different injection time, channel velocity, etc., calculations were done. Okay. Now that was old work done, but recently some work has come out. Came out. Fault get colder through transient granular wave. See, we were doing viscosity, which is more like a molecular kind of thing. But in a actual type, there are grains. So you can have additional eddies there generated. So rather than whole thing getting raising temperature by molecular processes, eddy viscosity, which takes longer period, so they will dissipate energy without raising temperature. So the fault will not get that hot if you take it to be granular and there are eddies involved in that.
But you can calculate the Reynolds number and decide whether it will be in the viscous regime or eddies will be important because you know the viscosity.
See, when we were doing molecular, no eddies, so the whole energy, mechanical energy
that
was
part,
getting there
right.
and or raising temperature.
Right, that part I understand, but whether the flow would be laminar or there would be eddies, because you know the viscosity, you know the channel dimension. Yeah. So what is your Reynolds number
laminar.
here?
We had taken laminar.
But Reynolds number is known in this case.
We did not, we took a laminar flow.
Right,
flow.
you did in the first problem and here they are allowing eddies.
Yeah.
But Reynolds number is known, so it should decide which regime you are in. Is it not so?
See, in the calculation, if you notice, we took a laminar flow.
Yes, that's what I'm saying.
I mean, one could have taken eddy viscosity there also.
Right,
At
right.
mu term, I could
Yeah,
have
but
taken,
let's say if mu is very high, because you know mu v by d decides ki what laminar regime may be maybe more applicable. That's what I'm saying. Depending
so,
on
see,
viscosity.
we
Yeah.
needed maximum velocity estimate. So
Uh-huh.
I don't think
You-
that is important. Important is that viscosity term. What will be the viscosity?
Yes, yes, yes.
So if you take a molecular viscosity,
Uh-huh.
then you are generating more, raising more temperature.
Uh-huh.
But if you take it a granular media and allow
Right, right.
some energy to get into the granular way,
Yeah.
so temperature may not rise that much.
No, no,
was
that,
the
that part I understood. Yeah.
But we didn't do that.
Okay.
We don't.
Okay.
We didn't do that. Now, then there is another paper came called resetting of by frictional heating in experimentally shear quadra. Our results indicate that high rate of frictional heating during thrashing event can reset geological clocks. Thus, the OSL signal in quartz from natural faults have the potential to directly constrain the age of system event. Whereas low rate frictional slip even longer over longer time does not reset signals in quartz. However, low rate can reset aluminum. I don't know that much about other things. But now there is also, I don't know much about OSL rating, etc. So, but the issue is that temperature could be raised to reset the clock. Okay. Now I come to a last part of my talk. I found it very interesting. There was a summary like this. A geological cross section of this landslide. Now, if you recall that Annapurna talk by Dr. So I also asked him what about role of temperature in that process. He said that while he went there, he didn't look at how the rocks were transformed, etc. So I found out a paper where say that high temperatures caused by shearing under high pressure conditions to exceed 800 degrees centigrade, at which point carbon dioxide started to be released by shear zone rock. So they find coated shear surface with superfluid. So so the kind of saying that but for this would have traveled much longer. So there is also big in landslide also the role of frictional heating is being included now. And the corresponding thing that before earthquake happens, there will be frictional coefficient will become almost zero. Sorry, slip will be very fast when earthquake takes place. So some of the landslide studies may help also to find out what kind of earthquake nucleation takes place at a great depth. Okay. Then there was another paper which I found interesting, the long run out of heating, pressurization, carbonate decomposition. And here think of shear heating, which depends on the velocity and sliding. This is raising temperature at the base of slide, then chemical reaction taking place, then pore pressure changing. It changes this E is changed, so this is changed back. So temperature changes, porosity changes. So there seems to be a very complex work going on where temperature is playing a big role, how these processes take place. So I hope I have been able to at least indicate to you that it is worthwhile to study also how the temperature is changing at the near the Earth's surface due to solar heat, changing cracks, breaking into parts, or looking at how heating at fault takes place so that the clocks are reset. Also, how the viscous dissipation takes place wherever there is a fluid motion or rock motion. So these changes, they may be very short duration, they are very sudden. That's why they have not been noticed earlier. Like if suppose you go to fault system where lot of studies are done, like San Andreas and all that, you will notice that heat flow anomaly which you get is very small. Don't get much heat flow anomaly if you go over this fault with heat flow measurements. But it looks that in steady state you will not observe anything. If you observe something, it will be transient, sudden. So so steady state transient heat conduction studies will be quite useful. I did not go through derivations of that because I think that if somebody wants to know, I can sit down and discuss in more detail. For everybody, I know many geologists are not fond of derivation studies, but you will not stop your physicists invading your field, so you may as well benefit from that. If you have any other
using this method. The sand dikes, they are dated using this OSL. Are there examples of people dating sand dikes using?
Actually, this work which I discussed, it has gone to Tyagi, Dr. Singhvi's student Tyagi's thesis has gone into that.
Oh, so you could actually date some of the sand dikes.
No. They were dating anyway, but a justification that your clock was reset by earthquake.
Oh, okay.
See, that justification. Your clock was reset by sand dike.
So they had got much younger date than they were expecting.
So you have much reliance on your technique. That yes, but the question was that this heating was so sudden that you will not observe it otherwise, but it can reset the clock because photons will respond to it. Mineral thermodynamics, no change in mineral vapor. That's why you see, if you go to Himalaya, you look at big fault, you find mound, you find some little bit rock and then say, yeah, this was faulty. Which is a mineral hota hai. So we used to study that earlier, but that was a steady state, large heat. So the problem was how to get, and also time period doesn't matter. Fraction of second is good enough.
Thank you.
But these parameters are, these parameters, as you rightly pointed out, that viscosity, we took the effect of confined pressure. What about temperature?
Yes.
Temperature could change it. And what about this eddy? I mean, we took mu strain square, rate strain square.
Right.
What about
eddy friction?
What about taking turbulent viscosity?
Yes.
So turbulent viscosity one could have taken. It's a eddy viscosity.
Right.
But it didn't offer that. It worked long time.
Okay, thank you.
Sir, if along fault we have some material like a fault gauge material or something which contain quartz, so that can we trace it for the last heating timing of that fault?
You will get only last heating only.
Okay, you will
Because
get the last
heating. Unless it has left imprint in some kind of rocks. See, if the heating was so much that some new metamorphic minerals were generated, then you can look at that. If you have repeated, then you can have repeated newer and newer minerals formed.
Okay. And one another question I have is like you're discussing like that sand dike kind of thing. So in the sandstone we are getting some columnar joints. Are these the result of these sand dikes? Can it be? In the sandstone we have the like this columnar joints in sandstone, and the sedimentary structure are preserved in that that joints also. So can it be the result of this or what? Like,
see, to form sand dike, you have to have a shear, some kind of shear, and then you have to perturb it, and then instability will grow, and so you find you have to ask some geologists, sedimentary structure geologists will know how to find what kind of structure it is. Is it depositional at the time, or it is post-depositional?
Like depositional sedimentary structures are preserved in that, but the outward surface or outer surface is a columnar joint kind of thing. And in the cross section also we are observing the columnar joints. And it is of extent of like half kilometer.
See, in order to do this kind of thing, I need that structure should be formed suddenly. If something, suppose you have a crack form and then material slowly fills it, I don't think that you will have
But
that kind of.
if it is like after filling, then how come it is sedimentary structure will be preserved in that? Yeah. But it is kind of connected to the beneath things. It is like 25 kilometer, like 25-meter high hill, and it is all columnar joints. Maybe, maybe you want to say that there is some igneous body beneath that or something like that. Yeah,
No, like think of basalt. In Deccan Traps, you get columnar
yeah,
joints.
that
They
is
are
common. That is,
cracks formed. But what I was thinking that you are filling something between columnar joint
yeah. Okay.
and dating that, not that.
No, no.
Columnar
Sandstone.
joints are, well, that is true about on ice how columnar joint comes. So it's a when things cool, when you think cool, there is a thermal strain generated, thermal strain. And as I showed you that when corresponding stress also generated, and when stress becomes more than the uh, some critical, then cracks start. And cracks I mentioned there were three types of cracks. So in here it is more like tensional K1 crack. So these are things worked out. I mean, generating a columnar joint, you have to have a cooling and contraction. Because of that, then you will get cracks formed. Actually, uh, about early earth scientists, when they wanted to build Himalayas and all that, they thought of earth is cooling, right? So the top surface of the earth will contract, and then wrinkles will be formed. So that was contraction hypothesis. Of course, there was an expansion hypothesis also, that earth is expanding, so some kind of wrinkles at the outer will be formed. Till the mantle convection and plate tectonics came, contraction, expansion were two popular theories, and many work have come out. The contraction of the mountain building was because of contraction of the earth. Ramsay, many old Jeffries, Ramsay, they wanted, yeah. See, the fundamental problem for earth is cooling, right? So in children also you say cool it, when so there is more energy, so you need to, you have to lose that. So any physical system with more energy cools it. And while cooling, it does variety of things. Like think of Earth. Earth is cooling, whether hot formed or cold formed. Because of decay of radioactive elements, Earth would have become viscous material, so it would have cooled. So say 0 to 100 kilometers, you get heat conduction. Below that, you get convection. Convection is much faster, right? Because you can ask why Earth is not only conducting, why there is no conduction from center of the Earth to the surface. Argument is that Earth will not be able to lose heat so slowly. After all, Kelvin and others took whole thing as a solid and cooled it. So by convection, you lose heat faster. come to the core. There is electromagnetic energy also. So more energy is being lost by electromagnetic energy also. So physical system is cooling itself, and in the process it uses various modes to get that heat off. Somewhere conduction, somewhere convection, somewhere magnetic action, some other kind of energy. But any system which has excess energy will cool, it will leave. Energy has to leave. And so contract for your columnar joint, you put more heat in a layer that will cool because it is in contact with atmosphere, which is lower temperature, so heat will be transferred. And in the cooling, you can generate thermal stresses, which will at regular, as some kind of polygon, this a cell will be generated, and
we have a tea break at 3 o'clock, so we have 20 minutes in our hand. So, yeah, 20 minutes. So, if anyone wants to ask question or initiate some discussion,
अभी time क्या हुआ तुम्हारा?
2:40.
So how are you going to prepare yourself with invasion of physicists? All those people who have geology background, so you have to question the tools which they have, because there has to be commonality in language. First thing is, if you can't read drawing, so you need to join them. Joining requires collaboration. Collaboration requires common language. So the language which they use, you have to learn. Now, I can tell from our history, we were not physicists, but in our group in Hyderabad, our guide was a physicist. Out of 4 people, 2 were physicists, 2 were geophysicists. So, when we have group meeting, they will say, this is not possible by quantum mechanics. And we never heard quantum mechanics. As a message geophysics, I never heard anything. They will say it's a quantum mechanics. So we started going to library and finding out what is quantum mechanics. So found out the language. So next time when they opened them out, we said that no, for our phenomena, quantum mechanics doesn't matter. For Earth processes, most of the cases I don't need quantum. Because then we understood what quantum mechanics does not have. If they were trying to calculate electrical conductivity of the core material, sure, quantum mechanics, because electron plasma, you can use quantum mechanics. So you need to know the language. And so language of language. Actually, this is the hard part. Language learning is hard part. Another thing which you need to do more computing. See, all of you do a lot of data processing. Similar thing goes into computing equations. So you don't have to read all those old mathematics. If you focus on computing and programming, nowadays I am told that Python programming is very easy. So all kinds of theoretical work can be done using Python. A lot of tools are available. So those people who have not come from this background, my suggestion is that forget analytical mathematics. focus on computing. And, that will be helpful.
Font ghost dating. I mean, could be thermoluminescent. Sorry, um, thermoluminescence. No. Low temperature thermochronology. So that would be
Oh,
include your fission track
You
and
have to ask tomorrow when Dr. Singhvi comes, because I hear people speaking about it that you have now low temperature.
yes, sir.
So actually, our temperature will have much more role. That see, then you don't need 500-600 degrees to get. If you have change of 100 degree, you can still use it. But then I'm told that you need other minerals with
Yes,
blocking temperature to find out.
Yes, sir.
Isn't
In that
it?
case, you use apatites or zircons.
Yeah,
And
right. So it is much more useful. It will be much more useful for that.
yes, sir.
See, earlier I will recall I used to see people who are doing radiation damage work. So they will have some temperature and relate to uplift rate immediately without doing any calculation. They will just transfer data. Whereas if you uplift and erode a rock, suppose your uplift and erosion is same rate, then the temperature profile is not uniform which you get. Calculation now show that you have better handle of interpreting your temperature, your measurement using correct heat conduction model than rough result. See, if you find temperature and say it is gradient and I relate it to uplift rate, but you can do detailed heat conduction model and then interpret your data using that. But generally steady state assume and
Question left. Any more discussion? Any more question? Tea is not there anyway, so. Okay, installation. That I can do. So I have messaged all the participants to this download Anaconda, and then I'll get it installed on their system. So if there is no more question, then I can do that in maybe 5-10 minutes. Then we can get a table. Right?